As you may know, the fourth state of matter is plasma. 99.9% of all matter in the universe is made of plasma. But how can scientists measure it? Well, for solids, it's easy. We can touch them, we can measure them with, say, rulers or calipers. For liquids, we can put them in a volume, or we can put a thermometer in them. For gases, we have pressure gauges. But what about plasma? Well, if you stick a probe inside of a plasma, you might actually alter the very data you're trying to collect. And while there are some traditional methods for measuring plasma, but oftentimes they're limited by the amount of electron density that there has to be, or sometimes they're just inaccurate. One newer way that we can measure these plasmas is called Coherent Microwave Scattering, or CMS. In simple terms, CMS works by firing microwave beams at the plasma to be studied. The oscillating electric field in these microwaves then vibrates the electrons in the plasma, which then emit their own microwaves that can be picked up and processed to understand certain characteristics about the plasma, such as its electron density. A more in-depth video about CMS can be found on the Purdue EPPL YouTube channel, titled Intro to Coherent Microwave Scattering. Researchers at the Purdue Electric Propulsion and Plasma Lab have been working with CMS in novel ways. More recently, Kenneth Reindersma, a master's student, has used CMS to characterize photoionization rates of oxygen and nitrogen in the low-pressure Thomson regime. But what does that actually mean? Well, low pressure in this case refers to how the experiment was in a vacuum chamber at 0.2 torr, or which is about 0.03% of atmospheric pressure. In this case, a femtosecond laser was used to produce the photons which then produced the plasma. A femtosecond is 1 quadrillionth of a second. To put that into perspective, 1 femtosecond to 1 second is the same as about 1 second to 32 million years. So a femtosecond laser emits pulses that last for an extremely low amount of time. They're used specifically in this application because they're so fast that there's no recombination during the photoionization process. Photoionization refers to the phenomenon of when a photon collides with an atom with enough energy to release an electron, which creates a positive ion. To understand the Thomson regime, it's first useful to understand Compton scattering. Compton scattering describes how a photon collides with an electron and then imparts some of the energy onto that electron, and the photon is then deflected with less energy. The Thomson regime is the low energy limit of Compton scattering, where the incoming photon has such low energy that there's actually no energy transfer once it collides with the electron. Kenny showed me around the lab where this photoionization data was actually collected. Check it out. Kenny, can you please tell us what we're going to see today?
All right, so today we will be going over the laser system that we have here, as well as the laser path that takes us towards our final system. And we have a vacuum chamber that contains our CMS system, which is for Coherent Microwave Scattering. So here we have is the femtosecond laser system that we'll be using. So on this side, we have a seed laser. The output of that is on the order of femtoseconds, and then it feeds into a pump laser system that we have here. And initially, before we're able to amplify the energy that comes out of it, because it is in the femtosecond range, going through the amplification medium would cause a lot of distortions and would result in a bad quality beam. So on this side, we have a stretcher that stretches the femtosecond pulse out into the picosecond range. And then here we have a nonlinear lasing medium that allows us to amplify the energy in the pulse, and it goes through this loop several times before it is then passed through the output on this side. As well as there's a redirection area where we have a small portion of the beam, about 1% of the energy is directed towards a photodiode that we can check on an oscilloscope over here to confirm that the laser is operating effectively. So, and here we have, this is the laptop that we use to control the laser system. It goes basically progressively up from the bottom as you turn on and you pass through the safety checks. An interesting thing as well is we have a MyTie controller inside of it, which essentially is a humidity and temperature controlling system for that nonlinear laser amplification medium, as it will absorb water, and if the temperature changes, it adjusts the energy, basically amplification properties. So it has to, all of these settings have to be controlled. So as we have the output of our laser here, there would normally be a mirror that we have in this spot in order to bounce it towards our final experiment. So it would come to this mirror, through this block, into this mirror, and then down to this other table here where we have multiple mirrors for a height and width adjustment to make sure that it's aligned properly. And then we have a thin film polarizer, which we are using to change the energy values that we have in our pulses, passing through a half lambda wave plate. And part of the beam would be passing to this beam dump here, and the other part that we're using would be bounced to this mirror, down towards this one, and finally into our lens and into the chamber where we assess the plasma volume. As well, for the laser system, we have 3 water chillers. 2 of them can be seen here, and then a final one back there, all for the thermal management of our laser system. And here we have, this is the power meter that we use. And nominally the laser is operated at 1000 hertz, which means you would take the power reading that you get from this and divide it by 1000. But during our experiment, we operate the laser at 10 hertz in order to avoid a memory effect caused by the gases heating up too much and not being able to equalize between pulses. What you'll take is the laser pulse will pass through this system, and then you will see a power meter on this in watts, and then you divide that value by the repetition rate to get the actual energy value in millijoules. And then as well, what we would have over here is we'd have two flip mounts here with mirrors on them in order to redirect the beam. We don't have a mirror in this one at the moment, but this one would be in order to determine our beam diameter, which is the total thickness of the beam before it is passed through the lens. And then we would have one after the lens focusing area here with another mirror onto a beam profiler, which we would use to figure out what our actual spot size is, as well as the beam quality and Rayleigh length of the laser. So here we have the oxygen and nitrogen cylinders that we use for our experiment, obviously attached to pressure regulators that we have here. They feed into a needle valve, and we use the Pirani gauge here and an ionization gauge to monitor our pressure inside the system. While we are running the experiment, we have it pumping continuously to try to encourage the highest purity that we can, as well as before we run the experiment, we flush it several times with whatever test gas we're using to push out whatever is left in there. As well, this is back here is the Maillard-Alpert gauge that we use that's connected to the ionization gauge. It only operates when we're using the diffusion pump, which is nominally only here in order to clean up the atmospheric gases that are trapped inside the microwave absorbing panels that we have inside. So you can see here the internal setup. These absorbing panels are used to lower the noise floor that happens when you're using the CMS system coming out of these gain horns here. So we'll have a receiving and transmitting horn. On both sides, we have these microwave absorbing panels, as well as a 200 millimeter lens that we used previously in order to decrease the spot size that we're able to reach, which increases the intensity. So here we have the oscilloscope that we use to monitor the signals that are coming out of our CMS system. The settings we have typically are some voltage range between 1 to about 100 millivolts. As well, the coupling for all of them is on DC 50 ohms, specifically for the microwave circuit that we're using. Almost all of these are matched networks. As well as we average our signals, so as we're collecting them, it's averaging 50 sweeps together of the same pulse energy. And then we have the microwave generator here with the output set to 15 decibels at 11 gigahertz. And now we can go over a brief overview of how the procedure will work while we're operating it. The first step is to plug in our roughing pump. And then we'll let that run for a couple of seconds, and then opening our chamber to the pump so that it can start lowering our pressure, which we will see start to drop on this Pirani gauge. It sometimes takes a couple minutes. Part of the reason why it can take so long to pump this down is the microwave absorbing panels that we have in there absorb atmosphere very quickly. So if we ever leave this chamber up to atmospheric pressure for more than about an hour, it can take several days to pump back down to operating pressure. When we were initially starting to run it, it literally took me and Nick, I think it was 3 or 4 days of straight pumping to actually even get it down to an operating region. I mean, if you think about the microwave absorbing panels had only ever been in atmosphere for their entire existence, and then you throw them in there and it's all right, this is gonna take a long time. And now we've approached approximately a steady state pressure here. Normally what we would do is we would let this drop down to 1 E negative 1 torr, which will allow us to turn on this diffusion pump that we have down here at the bottom. And what we'll use that for is to evacuate all of the atmospheric gases that are trapped inside of the microwave absorbing panels, because just using the diffusion pump or the roughing pump is not really suitable, as the pressure differential you can get is not high enough to evacuate all of those contaminants. Because with the diffusion pump, we're able to reach a pressure around 1 E negative 5 torr, which completely evacuates this chamber. But for now, what we can do, we can leave the roughing pump on, and then considering that this would have been evacuated and brought back to this pressure, we can use the test gas that we're using here, which is nitrogen in this case. Obviously, they are all attached with pressure regulators to ensure safe operation. We raise the pressure approximately above atmospheric slightly and have a flow controller here as well as a needle valve. And through these, we're able to monitor the pressure and regulate it until it is approximately stable. Additionally, while we were running it, we would have this flushed several times with our test gas just to ensure whatever is left in there while it's continuous pumping is the test gas we want. That's pretty much it.
So there you have it, a look at a real lab setup where CMS is being used. Kenny and other researchers have used that setup to tabulate photoionization data for oxygen and nitrogen. This is new data that's not been collected before. It's valuable to a number of fields, including gaseous discharges, high-speed aerodynamics, combustion, and filamentation physics. One use for this data could be to calibrate other diagnostic tools, with the photoionization data serving as an absolute measurement. A link to Kenny's recent paper can be found in the description below, as well as a link to the Intro to CMS video. Thanks for watching.